This is Introductory Physics Lab number 5, using Newton's second law to predict combined horizontal and vertical motion. I looked at motion that was similar to a projectile, which is a combination of vertical motion and horizontal motion. Since I don't have a cannon, I used a small ball rolled off of a shelf in a horizontal direction. My specific aims were to capture the motion of the ball with a video, analyze that movement in Tracker, collect and analyze the data from Tracker, develop a model in VIDLE using Newton's second law, then compare the actual movement with the model. My system was a light ball, and I centered the XY axis origin at the center of the ball just as the ball became airborne off the shelf. XY axis is tilted slightly to accommodate the camera angle. The negative Y is in the downward direction and the positive X is to the right. Surroundings are gravity and air, and I use the distance between the two shelves to calibrate a distance of 0.3048 meters. Assumptions were made was that the motion is only in the X and Y direction during the time interval. The only interactions with our system are gravity and air, and therefore net force is not equal to 0. This is a video of the motion. I graphed the X and Y components separately on this graph. Time is on seconds on the x-axis, distance in meters on the y-axis. As you can see, the x components graphed in a linear fashion, which demonstrate constant velocity, and the y components graphed in a nonlinear fashion, which show non-constant velocity or acceleration. I took some of the data from Tracker to plug into our computer model, the last time reading, the last y position, initial positions, and calculated the initial velocities. I also added in the force components, and here's where we put in Newton's second law to update velocity and then to update position. This is what the model looks like when we run it. And as you can see, the graph in the model is very similar to the graph with the Tracker data only. When I graph the model with the observed horizontal position, we find that the model superimposes over the observed position. You can see the observed position peeking out from under the light gray line right here, which shows that it's a very good fit. When we look at the vertical direction, we find that the model predicted that the ball fell faster than the observed when I looked at weight force only. Therefore, I calculated a B constant, force of drag, in order to correct the model to make it closer to what was actually observed. Here we see that the model fits very well at the end and at the start, but not quite so well during the middle. Potential sources of error are human error, video artifacts, the calculation value for B may not be exact, and there could be some motion in the z-plane that was captured on the video that is not accounted for. So what does this mean? For this type of motion, there are separate x and y components. The x component exhibited constant velocity, and that was demonstrated by the linear component on the graph. The y component exhibited acceleration due to the force of gravity, and that was exhibited by the nonlinear portion of the graph. When drag was added to the model, it improved the fit of the model, and therefore we can conclude that this model can closely predict this type of motion. And moreover, this provides more evidence of the accuracy of Newton's second law. So to summarize, Tracker was used to measure the projectile type motion of a ball. Computer model based on Newton's second law was used to predict the motion. FNet included gravity and the force of drag. The computer model was not an exact prediction of the motion, but very close. Possible explanations for the discrepancy: human error, B constant perhaps not exact, possible experimental artifacts related to the filming of the video. Thank you to my intro physics classmates and the Coursera faculty and staff.